in Bangalore who will speak on Brumer-Stark, some aspect of Brumer-Stark. Right. And don't forget to push buttons at the right time.
Yeah. Okay. So apparently I can use both sets of boards now. I just have to change the camera every time I go to the other board. Okay. But yeah, I was just looking forward to this conference for a while now. It's been in planning for a long time. So I thank the organizers for putting it together and inviting me to speak here. So this is continuation of Sumit's from Sumit's first lecture. So what I'm going to do is I'm going to give some parts of proof of the Brumer-Stark conjecture away from p equal to 2. And I don't know where Sumit is, but he'll do p equal to 2 in his second talk, and then maybe the plan is to sort of then tell you a little bit about equivariant Tamagawa number conjecture for Tate motives in the minus part. Okay, so let's recall what yeah, so some of the notations I'll just borrow from Sumit's talk and I'll not recall it. So here sort of the Brumer-Stark conjecture. So that this element theta st is in the annihilator ideal of the class group H minus part of it. So remember, F is a totally real field, and then H is a CM extension, finite abelian CM extension of F, and G is the Galois group. So okay, so that's what we want to prove, but the statement that the strengthening that we need is
you don't want to annihilate the S ideal class group. You want to annihilate.
Yeah. Okay. So that's bigger, right? Okay. So we can. Thanks. Okay. So this is some strengthening of the Brumer-Stark conjecture. Okay. So this, I think, again, was the statement mentioned in Sumit's talk. So I'll just recall it as it is. So the ideal of Zg minus that theta st generates is the same as the fitting ideal of Zg minus of this nabla, this Ritter-Weiss module. Okay. And as Sumit pointed out, it's important that two things are important. One, that this fitting ideal is principal, and second is that we have an actual equality. Because, I mean, although we want to prove that an analytic object is contained in some arithmetically defined ideal, which is like getting an upper bound on this arithmetic ideal, the method we use, Ribet's method, it only gives lower bound on these arithmetic modules on the Selmer group. So so using Ribet's method, you cannot hope to prove this kind of inclusion directly. You can only go in the other direction, and so it's important that we have this equality. And for the method to work again, it's important that we have principal ideal. So it's kind of very fortunate that this right object is found, which has a principal fitting ideal. Because in general, fitting ideals are far from principal, right? So this is the conjecture that Burns, Kurihara, and Sano made, as Sumit told you, and it's very fortunate for us that was already there. Okay, so the plan is the following. So I'll tell you a little bit about what this module is, some of its properties, in particular how it's related to Galois cohomology. So that's the first part of today's talk. And then once we reduce to constructing some cohomology classes, I'll sort of move to a different topic, which is modular forms and how to construct a cusp form that's needed for construction of those cohomology classes. Okay, so this is the Ritter. This module was first constructed by Ritter and Weiss without sort of these kind of decorations. So we just modify it a little bit, but it's Ritter Weiss module. And I'm sort of unsure how much details I should give. So anyway, what I'll see how it goes. Okay. So recall from class field theory that if FV is a completion of that at some place V, then we have the class module and class formation. So we have I'll just write let me stick to my notation, otherwise I'll confuse. So GFV and union overall HV over F. I mean, maybe I should write HW, but anyway, I'll just write HV. HV star. This is a. So I'll not explicitly write the generator of H2 here, but that I fix. But this is. I'll just say that this is a class formation. And similarly for global field, if I have again GF and H runs over finite extensions of F, AH cross modulo H cross. So this is also a class formation, right? So what I want to do is I want to get the Tate global Tate sequence and local Tate sequence in this, and then use that to construct my module nabla. Okay, so the fundamental class that I'm not putting in the notation, that gives you two sequences. So global Tate sequence. So for any finite extension H of F, I have so there's some module V and there's some module B such that this you get this, and then this thing is, as you all know, is isomorphic to ZJ. Right. So I'm using kind of notation from there if you like. And then similarly in the local case, we have HW cross to some local thing BW to Z to 0. And again, this thing is isomorphic to ZGW. Right? So local decomposition. Okay, and then the way these things are sort of set up, you you have a commutative diagram, the local global compatibility, and the way I would write it here is sort of I induce the module from GW to G this to, so that the choice of W over V doesn't really matter. So this is a commutative diagram of ZG modules. So what do I want to tell you next about this?
I think next you want to press the button.
Yeah, but until I figure out what I want to say, I'll keep it on this board so that people online can see it a bit longer. Okay. All right. So this is I'll think of this as a two-term complex, and then I'll think of this as a local two-term complex. But I'll put a bunch of local complexes together and sort of get a map between complexes and define the Ritter wise. Yeah, okay, seems to have. So, all right.
Sorry, what's V?
Yeah, so I mean, fundamental class gives you extensions like this. So there is some module V, ZG module V, and some ZG module B, so that you have this sequence corresponds to the fundamental class. Yeah, so, I mean, elements of H2 give you two extensions, so that is what that is. Okay. Okay, so I take S prime to be so large enough set containing, already changing notation, but disjoint from this set P. So remember, S was just ramified places which of F that ramify in H and infinite places. And I contain S, I take S prime, which is large enough. So what does this large enough mean? It just means that this class group is trivial. All right. So then I define the local V by putting all these these a bunch of places together. So what do? I hope I get this right now that I've changed the notation. So I take for each V in S prime, I just take the original VW. And for everything which is in T, I take the principal units. So these are principal units. So elements of OW. Okay. So and everything that's not in S prime or T, I just take so this is OW. Not in. Did I say no? Yeah, not in. I think I said not in. Thanks. Okay, and then for the B local, I just take yeah, I just take V in S prime. And that's it. And at the other places, I just take 0. So that's what this means. So I have this two-term local complex. I think this is in degree 0 and degree 1, if I'm not wrong, but you'll see. And then the global complex is just V to B, and that commuting diagram tells you that there's a map in the local complex to the global complex, which I denote by theta. So okay, and
So it should go the other way, right? The global flow.
no, I think this is right.
Okay.
And then the Ritter-wise complex, I just denote as you take the mapping cone of theta, and then you shift it by -1. Okay, so that's the complex. Okay, and so where does nabla come in? So sorry.
No, you're right. I was confused. Sorry.
I have all my S's and T's. So one thing is that this doesn't depend on S prime as long as you take it large enough. So this is why you won't see it in the notation anywhere. So that's something we prove. And the Ritter-wise complex that. So earlier, this is defined to be the first homology of this complex, but let me tell you a little bit more about this. So maybe this is not very eating, but I hope once I write down a long exact sequence, it will be. So here's the proposition. So H0 of this Ritter-wise complex is just OHST star. So these are all such that X is congruent to 1 mod T. Mod T just means modulo every prime in of H above T. And then H1 is what it is, and H2 is 0. That's all you need to say about this. So, okay, so how does one do something? I mean, yeah, so this is not hard to prove. Let me just write down you just unwind what the definition of this thing is, and you get a long exact sequence like this. So you get H0 of this. This goes to all places of H which are above places in S. So I write that as SH, HW star cross all places of H which are above places in T, UW. So those are the principal units. And then at other places, you just have the unit. So this is all W, which is not in SH, in TH. So that comes from your V. And then that goes into H cross module, H cross. So that comes from your V global. And then that goes into H1. This thing that goes into product over all. I'll move this board up in a second. SH copies of Z, and then that goes to Z. I mean, that goes to H2, but that's so that's what this is. So it's not so it tells you that H0 is what I said it is, right? And H2 is 0. Moreover, it gives you that this nabla lives in a short exact sequence that we saw in. So let me erase this, and then I'll move the camera. I have to wait until it tries. I'll also erase that. Okay, so that it's a corollary. You get that. So if you see what the co-kernel of this map is, that will give you the ST class group. So you have a short exact sequence like this. And that by definition is this nabla. And then you get this X Yes. So this is by definition the kernel of this thing. You take the free abelian group generated by all places above H and you take the elements of degree 0. So this is kernel of. So these are all the familiar objects that we see. Okay, so we saw this and sorry about this. All right, so that's 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 your nabla, and that's one property that I wanted to tell you about that we saw in Samit's talk, that how you get this short exact sequence, how nabla captures information both about the class group and about well, not quite units, but some places. All right. So the next thing I want to tell you is just give you a statement of the theorem that tells you how this nabla is related to Galois cohomology. Let me start writing and see how it looks. Okay, so so again, this theorem Samit mentioned in his talk, and let me write it slightly more precisely, but it will still be somewhat vague. So for a G module A, G was this again Galois group of H over. So those notations we have already fixed. All the continuous G homomorphisms from nabla A we want nabla or nabla minus. Let me write it then. So these are in 1-to-1 correspondence with tuples. So A also has a Galois action and will be in S. So what are these? So kappa is where kappa from GF to A is a 1 cocycle with the following properties such that, so a bunch of things. So kappa is unramified outside T.
That means like the cohomology class represented
Yeah.
by kappa is
I was
unramified.
going to say that. So okay. Right. So that means that the cohomology class that kappa represents is unramified outside T. It's locally trivial at S. So again, I mean, all those things mean what you know for the cohomology class represented, right? So is so these are the things that you would expect from the class group anyway, right? I mean, what is this class group? This corresponds to extension of yeah, and it's sorry, let me write the third. And two more things, but let me write this first, is tamely ramified at T, right? And so what does this class group correspond to? This corresponds to extension of maximal abelian extension of H, which is unramified outside T. and all primes in S, all primes above S split completely, and it's at most tamely ramified at T, right? So you would expect this sort of property from this. Well, moreover, I think okay, so not only that, I think what are these XVs? So this is the Frobenius. This should be sigma V minus 1 times XV. So this is Frobenius at V. So for all V in.
I think it's for all sigma in GV, right? Like a local.
Oh,
split,
yeah.
a local splitting of the cycle.
Right, yeah, this. Oh, yeah.
So you don't want to.
Yeah. For all sigma. For all V in this, yeah, so. Oh, so, above sigma V. No. Yeah, oh, okay, I think, yeah. Sorry. Don't know why. What else? Yeah, and then, so, well, this is not really sort of what I want from kappa, but under this correspondence, so I don't know, maybe further. So F from in form nabla TSH to A. Yeah, this is really bad.
Yeah, there's nothing that can be done about that. I mean, is it?
Well, I don't have a dry.
Oh, that's not dry.
These are both wet.
They're both wet.
This is like a cheap substitute of one
let me-
system. I mean, if we were still in EU, they would ban this. That's why we are not in EU. Sorry, this is being recorded.
Well, yes, it is. Well, okay. I think Ian's going to try and find.
All right. Fine. So,
You're taking all cocycles, not one representative for each cohomology class.
no, so homomorphisms correspond to this. I mean,
I mean, you have to mod out by an equivalence relation, I guess, is what. Right. You have to talk about when two tuples are equivalent. Modulo. And it's kind of like modulo being equivalent by a co-boundary that adjusts the exits accordingly.
yeah. So am I?
It's right. It's one-to-one correspondence with tuples modulo an equivalence relation on the.
Right. No, but then I don't want to say it like that. Okay, so rather than sort of telling you what the equivalence is, let me just sort of modify the statement, which is enough for me. So,
Modulo correspondence.
yeah. So giving an element in this, sorry, to give an element in this, to give an element in this, it is enough to find kappa like this. Then I don't need, I mean, that's enough for our purposes. Then I don't have to talk about this equivalence. And further, if F is given by tuple like this, then image of F is generated by kappa of GF union XV. All right, so So this is, I mean, yeah, I don't want to say anything about the proof of this. It's not going to be very illuminating, I think, at least not the way in which I can explain. So, you just have to sort of, I mean, do the, yeah, I would say like unwind the definitions, but it's takes a while to do it. So, okay, I'll not say anything about the proof of this, but the upshot of all this is the following. Is so remember, what do we want to do? So recall, we want to show that fitting ideal Zg minus of nabla ds h minus is contained in theta st, right? And the other another property of fitting ideals that Samit mentioned is that if you have a surjection from M1 to M2, then fitting ideal of M1 is contained in the fitting ideal of M2. Okay, so so if we find tuple, yeah, okay, but yeah, if we find a cohomology class, kappa in of cycle, because I stated things in terms of co-cycle. And XVs in B such that all those properties are satisfied. That 1, 2, 3 are satisfied for this. And B is generated by kappa GF and XVs. Then we get a surjective G module homomorphism from nabla. Now, I think I said I was worried about whether I want minus here, so I will. I think everything we do is on the minus. So we have a surjective homomorphism here. So if further we can find the fitting ideal of B and show that it's contained in this, then we are done. So that's the upshot of this theorem. So we have reduced our work to finding a module like this with fitting ideal contained in theta. So we want a large enough module like this and construct a cohomology class, a co-cycle with values in that. So,
Theorem is still true as stated with the minus sign then?
yeah, it's
So I think you want the module to be a minus.
yeah.
You want
Which one?
like B or an A.
Yeah. So it's a module of did I
Require the complex conjugation acts.
acts by -1 on this? Yeah. So this is a Z minus module, right? Everything is on the minus side. Sorry. Don't even know if it's moved or not. All right, and so now we are kind of in a good situation because Ribet's method tells you exactly how to construct such objects. A global cohomology class with prescribed local properties. So that's kind of the starting point, and once you get to this point, you sort of start thinking that okay, you can prove something. All right, so okay, so now I'll tell you about the modular forms input that we need. And maybe I'll not. Yeah, so I'll tell you about the Eisenstein series that we use and perhaps get to the construction of custom. What we need, and then the rest of it will be good. So I'll not tell you, I mean, I'll not introduce the notation for modular forms. I'll just tell you the modular forms that are the Eisenstein series that we are using. Yeah, so it should be more or less familiar. So so if n is an integral ideal of f, then I'll denote by m sub k and psi sub k and psi sort of modular forms of level n and Neven type psi and plus forms like this. So we'll start with some Eisenstein series and then construct an element in the cuspidal. Okay. So we identify these modular forms, or I write them down just in terms of their Q expansion at infinity. So so giving an element here, I'll just sort of say that it's given if I tell you what these things are for each lambda in the narrow class group of F, and for each non-zero integral ideal in OF. So we'll just sort of talk in terms of Q expansions at infinity like this. So okay, so here's the Eisenstein series that we are going to use. So I'll denote it by E sub k psi 1. So psi is a character of G with the same parity as K's. These are all parallel weight. And so what are the non-constant terms of this? These are exactly what you would expect them to be. So all A dividing M psi of M by A norm of A to the K minus 1 divisor sums. Think, and then the constant term is somewhat complicated. Okay, I wanted to reduce to simpler situation, so I'll do it after I write this thing down. So this depends on what k is. So k here is bigger than or equal to 1. So this is 0 if k is bigger than 1, and modulus of psi. So psi need not be primitive, right? So consider it with some modulus. Modulus of psi is not equal to 1. And it's, so everything is scaled by 1 to the 2n. Remember, n is degree of f over q. Yeah, psi inverse of lambda L psi inverse 1 minus k if is bigger than 1 and modulus of psi is 1. So Yeah, so the constant term is somewhat easier if the weight is larger than 1. And in weight 1, you have a somewhat complicated thing because, you know, ek psi 1 is same as, so E1 psi 1 is same as E1 1 comma psi. Okay, so this is L psi 0 if k is equal to 1 and modulus of psi is not equal to 1. But if modulus of psi is 1, you get two terms. You get this plus psi inverse of lambda L psi inverse 0 if k is equal to 1 and modulus of psi is equal to. So that's the Eisenstein series. Now, okay, so I want to simplify the situation. So from now on, assume that H over F is unramified. So hence S is just S infinity. These are just infinite places of F. E is some non-empty set disjoint from the Archimedean places which satisfy this Deligne-Ribet condition. So the reason for this is if I mean, so in general we have to change this set S and T because we cannot do the modular forms construction with the S and T that we have been using. That doesn't mean that we did not prove the theorems that were claimed, but going from this modified SNT to the SNT we want is a sort of non-trivial amount of work, as Christian will tell you, or as a sort of he proved it directly from our result, but we can also do it using ETNC. So all the theorems are fine. It's just that the modular forms construction works with a different choices of S and T, and then we have to sort of go back to our original choice of S and T, and that requires some work. So it's just easier for us now in this lecture to just assume that H over F is unramified. This aspect of how trivial zeros come into the picture, it happens here as well. So that's the aspect I want to explain. And so that won't be lost by the simplifying assumption. Okay. So these these Eisenstein series, they live in the group ring family. So what I mean by that is, I'll just write down some formal elements in the in group rings and tell you that that's and it will be clear that interpolates the Eisenstein series I wrote earlier. So if I so from now on we'll have the simplifying assumption. So this bold psi will denote this character which goes to the narrow class group of conductor 1 to G, and then this goes into ZG cross or minus that. Yeah, then I need to take K with the right parity. But the group ring family I'll just denote it by this. And what is this? Again, I'll just sort of tell you what the Fourier coefficients are, and that will tell you what my Eisenstein series is. Then, so this is A dividing M, bold psi of M by A. Everything is conductor 1, so I don't need to worry about anything else. And then, as usual, the constant term is a bit more complicated, but now everything is conductor one, so I won't have as many cases to write down. So that's good. So again, everything is scaled by 2 to the minus n. So psi inverse of lambda theta 1 minus k. So this is the theta, this is the Stickelberger element that interpolates values of functions of characters at 1 minus k. So this is if k is bigger than 1, and of course the conductor is 1. Right? So everything is fine. And then because I'm writing it like this, I'll start denoting my theta. Okay, I'll tell you what this theta is and what the other. So this is theta 0 with a hash on top, and then this theta 0. So let me tell you what these things are. Yeah.
Remind, what is G1 plus?
That's just the narrow ray class group of
Okay.
of conductor 1.
Okay, thanks.
Okay, so theta so theta minus k, this is theta st of 1 minus k, and what this does is for any chi you get L, so st, this is L st chi inverse of 1 minus k. So that's the so this is in ZG if appropriate condition on T is satisfied. And so similarly for K equal to 1. So that's what this 0 means. And
You haven't done anything at T for your Eisenstein theories.
I haven't done it. Yeah, right.
You really want MT.
Oh, yeah, sorry. Yeah, right. You're, thank you. Yeah, I have to do. Okay, let me do this and then not worry about where this lies up. I mean, I can also do that here. So this is the map given by C-linear map given by G going to G inverse. So I can apply this. And what is theta of 1 minus k? This is just theta s infinity and then empty set 1 minus k. Yeah, I haven't done anything at T, right? So these things lie in QG because of Ziegel and Shintani's result. Yeah, I have to do the T modification. That's what I'll do next. Start at 10 minutes. Oh. Did I move the? I don't remember now. I moved the camera to this board. I had forgotten to move the
Oh, you
camera.
forgot to move the camera. Well, I mean, maybe
Anyway, sorry. So this is
you sort of scream if there's someone online can yell.
okay.
Henri, can you see the camera? Can you see the board?
Yeah, I know it's labeled, so now I know it's the right.
Yeah, I can see, yeah.
Okay.
Never mind.
It's all boring calculations anyway. So, yeah, now we have to do this T modification, and the way this is done is as follows. So let T be product over all L in T of these primes, and then I'll have the modified Eisenstein series. WK psi 1. So this thing is summation m dividing T. You take the Mobius function. So it's -1 to the number of prime factors that m has, and psi of m, norm of m to the k, ek psi 1, and you level raise it to, yeah. Okay. So all these things were level 1 before. Now you have level raised it to m for various prime for various divisors of m, you get a level t. For various divisors of t, you get a level. So all right, so these also, so you can show that these also live in group ring families. So WK they sort of are put together to give a group ring family. WK bold psi 1. I mean, you just you change this by the group ring sort of bold psi m, and you change this by the group ring family, and you show that that thing interpolates the W's that you want. So it's like a small calculation to do. Everything, at least you see, write it down and it makes sense, and then that's the right thing anyway. So this is in MK. So what? And the constant term for that is are these things with t's in them. So
You never really said what a group ring family of modular form is, really.
no, as I was saying, I mean, most things about modular forms I'll assume, but yeah, but it just means that when you specialize this psi to a specific character, you get a modular form with that Neben types. The same way. Okay.
Or mean.
That's level raising it too. Okay, maybe I think this is a good point to stop, because I want to take some linear combinations of these and then tell you what a cusp form is, but yeah, I don't think I can do it in 5 minutes. So maybe that's a good point to stop, and I'll pick up here next time.
Okay, all right, let's